that those rules don't work. They do for Gen Chem. Where they don't work is for OChem. Okay? Ask your Gen Chem instructors how many of them liked OChem. Okay? Next time you take 151, 152, anywhere you go, ask them, did you like OChem? Usually the response is an overwhelming no. They hated it. Why? Because they didn't know how to freaking draw structures, and yet they're teaching you how to draw them wrong. That's why they don't know what they're doing when it comes to structure. Right? That's why they suck at it. Right? It requires practice, and it requires a proper understanding of those structures and how to put them together. These rules allow you to get to that understanding. Okay? The rules put forth by the textbook don't necessarily take you to the wrong structure. They get you to the correct structure through wrong reasoning, and that reasoning hurts organic chemistry. You don't need organic chemistry. Come up with whatever rule set you want to get you the correct structure. If you need OChem, you should be following this. Okay? That's how I would look at it. Kind of, sort of? Kind of, sort of. We even got a repeat. The next part that comes with it is this big shape table summary thing. Okay? Your primary focus on this shape table summary thing is down here. Okay? That is your primary area, because that's where most of our structures are going to come into play. Okay? The rest of the structures and shapes could come into play up above, but for the most part, that's what we're looking at. Okay? To interpret this, you have to have a Lewis structure. If you don't have a Lewis structure, you can't do this part. Right? That's why they're sequenced that way. Okay? Which then gets us to some practice. Okay. First thing I want to address is this system right here. We're going to take a look at that. Because that one right there is stupid. The textbook asks you to do it, and it's dumb. Okay? It's looking at the Lewis dot structure for an atom. Utterly meaningless. Okay? But where it goes to is a system that is taught, which is horrible for structure. And we'll walk through that. So, carbon. How many valence electrons does carbon have? Okay? So we got a couple different answers shouted out, which is good. We got two answers, 6 and 4. Okay? 4 is the correct answer. Carbon has 6 electrons. For the record, we now have a periodic table. Ta-da. Okay. On that periodic table, we can see the atomic number for carbon is 6. Since it is neutral carbon, how do we know it's neutral?
There's 6 protons.
Why do we know it's neutral when I asked for this? Okay. The balance of electrons or electron information is stored in the upper right-hand corner. Since there's no number written there, it is assumed to be 0. Which means when I add up the charge of my protons and electrons, it equals 0. Because protons are positive and electrons are negative, I have to have the same number of electrons as I have protons. Yeah? So we could say carbon has 6 electrons, which is valid. Okay? But when you go to meet somebody, do you reach into their chest to verify that they have a human beating heart? No. You just kind of assume that. You assumed they weren't a robot. Okay? We don't make that, we shake hands. Hi, how you doing? We have a conversation. We deal with the outermost stuff. We don't care about the inside for the moment. Same thing's going to happen for atomic structure. We care about the valence electrons, the outer energy electrons. Those outer energy electrons can be found by looking at the electron configuration and specifying the highest energy level. For carbon, it is 4. How do we know that? Well, we could draw out our electron configuration. 1s2, 2s2, 2p2. There it is. Highest energy level would be 2. How many electrons in that one? That would be 2. How many electrons in that one? 2, which means 4 valence electrons. How many of you are comfortable with electron configurations? Half the class, that's not too bad. It would be nice if there was a faster way to figure out your valence electrons, right? How do we figure that out? You read it off the top of the periodic table. Okay, we have groups and families. Within a column, they all react the same. Why do they react the same? They have the same number of valence electrons. So we can go to the top of that column, and for carbon, there are two numbers written up there, a 14 and then an IVA. If you take a look at the periodic table that you have on your exam, your practice exam, it gives you that 14, and then it also gives you, please say it says 4A, and then just says 4A, which means you don't have to interpret Roman numerals. All you got to do is read 14 or 4. What do 14 and 4 both have in common? 4. How many valence electrons does it have? 4. Just read the number off the top of the periodic table. That is now your valence electrons. Okay, so I have 4 valence for carbon. I need to pick a central atom. It's kind of a dumb thing because there's only one atom. So it's going to be carbon. And I now place electrons around the most electronegative. Well, there's only one atom, so it still doesn't matter. I'm just going to place them around there. According to the rule set I said, we do it in pairs. Okay, we do it in pairs because we're trying to make bonds. Can we have a bond if we have only one atom? No, so it's a dumb system to look at, again. Okay? And the way you'd be taught to do it would be place them singly around the carbon. That's how you'd be taught to do them. Interestingly enough, they're on the faces of a square. Okay? Each of those faces now represents a place where you could put electrons, or a group. Okay? And what we've now drawn is the Lewis dot structure for carbon. You seem super impressed by that. That took like years for someone to figure out. You guys just poo-pooed it right off the bat. What if we did hydrogen? How many valence electrons? 1. So if I looked at hydrogen, 1 dot. This is what people go through and do. Oh, dot, 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 dot. This is what I like to call the Lego model of Lewis structure. Okay. What Lewis structure is a potluck. Okay. We all go to a potluck party together. What do? It's going to that potluck. You bring something. You bring food. All of our atoms are bringing something to the potluck that is this molecule. What are they bringing? Electrons. According to this theory, when we put the electrons down, I immediately get to take my food. Okay? So if we all brought food in, you could only eat your food at a potluck. Does that make sense? No, it's pretty stupid. Right? Okay? We add to the next level behind this. You can only eat the same amount as everybody else. Does that make sense? Somebody will be like, yeah, really? I'm going to eat the same amount of food as, who's the smallest person in this room? Okay, probably you. Okay, I'm going to eat the same amount of food as Lisi. Yeah? Does that make sense? No. Okay. Who's going to eat more food? Me. Bigger, stronger, I don't know about that part, but I'm definitely bigger. Okay? And I have a bigger stomach, I can eat more. So I'm going to consume more of that food. Who's going to be first to eat? There's someone that's interesting. I'm going to be the first one to eat. Why do I get to be the first one to eat? Could say I'm hungrier. I'm the boss of the class. I get to eat first. Okay, there's a priority behind who gets to go first. Same thing's happening with our elements. They're all consuming those electrons, and they're consuming them according to their individual desires and their max capacities. So when we go through and look at this structure, we're going to end with the exact same process or the exact same answer, but we move a slightly different route. Carbon comes in with 4. Hydrogen comes in with 1. There's 4 of them, which means 8 electrons. Carbon's my center atom because it's the only one that can bridge. I'm going to scatter my hydrogens around that carbon. Notice, where am I scattering them? On the faces of a square. I now want to go through and place my electrons. I want to place my electrons on the biggest, strongest, meanest one. How do we define biggest, strongest, meanest in atomic language? That's the electronegativity. Carbon is more electronegative than the hydrogen, so I'm going to place electrons around the carbon first. Hungry, hungry, hungry hippos. Thank you. We now have our electrons distributed. Wherever there's a pair of electrons between atoms, I'm going to convert that into a line. Line, 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 line. Now I will check octets. Do all atoms have 8 electrons around them? No. What do you mean? they don't have any dots. What does a line represent? 2 electrons. So there are dots there, but we've changed the meaning to represent bonding electrons as opposed to non-bonding electrons. So we've changed our representation to show different meaning. We would never do that in the real world, right?
Don't they have to have the dots all the way around? At least
Like,
the other 3 sides?
I see where you're going. We'll get to that. A versus B, right? Change the symbol doesn't change the meaning, right? An A is the same thing as a B? No. Okay. We change the symbol, it changes the meaning. Okay, we're trying to show meaning by changing it. Okay, which is going to get at a pet peeve that we'll address in a little bit too. There's lots of pet peeves in this one. Sorry. Okay? There was a suggestion that there aren't 8 electrons around all of the atoms. Okay? And I believe what I was hearing was that I don't see dots around the hydrogens. Okay? So really what you're stating is that the hydrogen doesn't have 8 electrons around it. I like that. That's good. Does the carbon have 8 electrons around it?
Yes.
Yes. How many electrons are around each of the hydrogens? 2. So I don't have 8 electrons around the hydrogens. It says octet rule. We say, or you'll hear me say it. It's octet for a reason. We need 8 electrons. Except hydrogen. Why except hydrogen? Why can it not fit 8 electrons?
Because they only hold 2 in its valence.
If you look at hydrogen's electron configuration, the energy level that hydrogen is in fits how many electrons?
1.
Energy level? 2. If we look at every other element, they will hold 8 or more. Why was the focus at 8? Lewis was primarily an organic chemist. Organic chemistry simplifies the periodic table. We look at the second row. We delete most everything else. And we look at the second row, how many electrons fit in that row? Rhymes with fate. 8. There are 8 electrons. That's why it's an octet. Hydrogen can only hold 2, which means, do those hydrogens have 2? Yes. I don't place more electrons around them. I can't physically put those electrons on the hydrogen. So does every atom satisfy its octet? Yes. Carbon has a traditional octet. Hydrogens have a duet. They sit at just 2. We now have a Lewis structure. Is that any different than the Lewis structure we drew before? No. It's the exact same answer. Okay? But the meaning behind how we did that was drastically different. In the other place, we snapped them together like Legos. In this case, we said the electrons need to go in this place, and then we disperse around. That subtle change is so big that it literally takes 2 weeks in organic chemistry to stop people doing the Lego method to get to actual organic chemistry. It's a huge issue. The Lego method belongs in elementary school or biology. Okay? There's still lots of cool biologists. Don't get me wrong. There's still lots of good stuff there. They should stop talking about chemistry. Okay? Kind of, sort of?
Will this be accepted in other biologies and chemistries above this level?
So that what's lovely about this is that this is correct. The instant someone says it's not correct, they're full of something, and you can use a shovel to deal with that. Okay? And if you would love to direct them to me, you can. And I will lay into them for their misunderstanding of the subject. Because I have no problems with that. Okay? So, yeah, scientists, egomaniacal, right? We talked about it. Okay? The answer you get is the same. The understanding for why you get that answer is what changes. So the answer at the end, yeah, it's going to be accepted because it's the same answer. How you get there becomes the problem. Okay? So let's try one that's a little more challenging. SO3. Okay? Take a look at SO3. How many electrons does sulfur have? How many electrons does oxygen have? 6. Interesting that you answered both of those questions correctly, even though I asked a crappy question. What was implied? How many valence electrons, right? Please reconnect. Thank you. How many oxygens are there? How many total electrons do I have? Try again. 24. There were 18 from the oxygen and another 6 from the sulfur. Where's my center, or what's my center atom? Sulfur. I will now scatter my oxygens around that sulfur. Yeah? Valence electron, or sorry, don't do that. Not valence electrons. Now I need to place electrons. Where am I going to start placing those electrons? Around the oxygen. Okay? Notice I'm going to start placing them between the oxygen and the sulfur. Why? I know I'm going to have to put a bond there. So that's why I'm starting placing them there. How many electrons have I drawn? I got 24. All of my electrons are now in my drawing. Right, so now what I'm going to go through and do is anywhere I have a pair of electrons between atoms, I will convert that into a line connecting those atoms, and I now have bonds, yeah? Say it again? So, step 6, satisfy octet by moving pairs. Do all of my atoms have octets? The sulfur only has 6 electrons around it. Does it have its octet? No. It needs 8. Has to have an octet. Okay, so there's a couple approaches to this that can need to be mentioned and you need to be aware of. Approach number 1 that a student will typically go through and do is go, well, dang, it needs an octet. What's the problem with adding 2 more electrons? According to my total, I had to have 24. I've now put 26 in. That's an invalid Lewis structure for the formula I was given. Okay? So that's failure 1. Don't add more electrons. You have to use the electrons that are already there. Okay? So you could take them away. So we could take 2 away from the oxygen. In this case, I'm picking the rightmost oxygen. Notice there's a hole there now. Okay? And we could place it here. I know you didn't say that. Okay? But look, I just moved the 2 over. Now sulfur has an octet, yeah? Yeah. Does the oxygen? No. So what you were suggesting is a fantastic idea. I need to place those 2 electrons where both atoms have access to them. I will place them in between. The instant I've placed them in between, what have I created? A bond. Okay? And in particular now, we could call it a double bond. Ta-da! There's the existence of a double bond. Guess how it comes about in the other method? Well, this doesn't work. Let me just start doing stuff until I get the right answer. The only reason you know you've gotten the right answer is
When you satisfy the octets.
when you knew what the answer was. That process for solving a Lewis structure is dumb. You don't know the right answer. That's why you would have to move through this process. So if we go through and look, we've now satisfied octets on all atoms, yeah? Okay. So I'm going to rewind back a little bit. Okay. Actually, I'm not going to rewind back. I'm going to draw that again. Over here. Here we go. Dot, dot, dot. Everybody agree? Have I drawn the correct structure again?
Yeah.
Cool. So now we're going to rewind back. You removed those electrons from that oxygen. Were there any other electrons you could have had access to? Yes. Okay, we could have pulled those, right? What would your drawing look like? Exactly the same, which means it's the same thing. I don't care. Okay? I could have also looked at those. Exactly the same. Don't care. How about these? Okay. If I did that, what would my structure now look like? I would now have a double bond up there. Does that look different than the one I've got in black? Okay, a little. I'll accept a little. Okay, yes. Which one is correct? They are both correct. Okay. One of them is not correct. both of them is technically more correct. Why only more correct?
Because you need to show the options, the possibilities.
There was another oxygen that could have shifted those electrons. So if you were asked to draw the Lewis structure for this particular formula, SO3, you can't draw just one. You would have to draw them all. And because I just recently thought of this as a horrible joke, it's just like everybody's favorite game, Pokemon. You got to catch them all, right? You could boo, that's okay. You'd have to draw all three. You draw one, you're a third correct. Okay? Is a 33% a good score on the exam? No, so do better than that and draw all three.
So if it was like SO8, does that mean there's 8 different possibilities?
Oh, interesting connection. No. Okay. So the question, just for the record, because I don't think that got recorded, or maybe people in the back. What if it said SO8? Does that mean I have 8 different ways to draw that? No. That was a completely random and arbitrary connection. Okay. So just because there's 3 structures, it's not because it says SO3. Okay? And I can come up with a counterexample with that very, very quickly, which I'll walk through because it'll add some more information. Okay? So does that make sense? If we follow the old method, you're just like, well, I need to make a double bond, so here's a double bond. Do you recognize that you also could have done it at any one of those other locations? Usually not, which means you don't see resonance. How important is resonance? Second semester OChem, 70 to 80% of the time, when asked why, the answer is resonance. So when people don't understand OChem, it's because they didn't understand Lewis structure. Okay? So it's an important concept to deal with. It does kind of suck. It's difficult. I'm not saying it's easy. But this establishes the baseline that allows you to get there and be able to build further on. Kind of, sort of?
If you took like the left oxygen and had it on the bottom, and then did all 3 for that, would you have to draw like?
I should have shown it in a different color, so I'm going to draw it in a box here. Is that blue structure a new resonance structure? No. So when trying to go through and draw resonance, pin your atoms. Okay? So you'll notice in the 3 that I've got drawn, the sulfur's in the middle, we got the 2 oxygens left and right, 1 oxygen above. That's the same in all 3 cases. Don't start rotating structures, because that's going to make life miserable very, very fast. Okay? If you had initially drawn it top, bottom, right, that's fine. You would still get 3 resonance structures. Okay? But they would all be top, bottom, right, within that central context. Does that make sense? Yes?
What's the exact definition of resonance?
Resonance is that there's multiple ways to distribute the electrons in a molecule. Okay?
Is that important to us in this class?
Kind of like a knife in the chest. No. Is it important enough that you'll see questions like this on the test? Yes. If you got it wrong, would that mean you don't get an A? No. Okay. Some people that have been coming into class have been asking some very pointed questions that are very challenging. Okay. The ionization energy example that we walked through, that's an A-level question. Resonance, A-level question. Just because you don't get all of the A-level questions right doesn't mean you don't get an A. Some you can get right, some you can lose. Does that make sense? So you got to decide where your comfort level is and where your threshold for, oh my God, I've got to have an A. If you got to have an A, do the best you can to get every little nitpicky detail down. If all you need is a C, I still think you should learn some A-level questions, just because you will probably miss significantly and you might end up getting a D, and that's bad. You want an A, perfection. You want a B, aim for an A. You want a, what's the next one? C, aim for a B. Okay? That way you get a little bit of wiggle room. Make sense? Okay. Should we do another one? Yeah. A little bit more complex. Adds another little layer on top of this, but it's fairly similar. SO3 minus 2. How does this change our system? I have no idea why that did not erase. And it is very difficult to erase because it doesn't show up on my screen. How many electrons does sulfur have? How many electrons does oxygen have? How many oxygens? 3. Wouldn't this just be 18 again? By 18, I meant 24. What does that minus 2 mean?
There's a negative charge.
There's a negative charge. To be negatively charged, what do you need? More electrons. How many more electrons to get a negative 2? 2 more electrons. So when you see a charge, what I would typically do is write charge as an extra piece at the bottom. And in this case, I want to add 2. That becomes challenging. I'm adding 2, though my charge was negative 2. Why?
Electrons are negative.
Electrons are negative. So we have to watch out for that minus sign messing with our calculations. How many electrons total? 26. We go through and draw this out. Sulfur. Oxygen, oxygen. We'll shift to the suggestion for the other format. Okay? We'll deal with the box in a second. Okay, placing electrons, starting. Oxygens, 2, 4, 6, 8. More numbers. How many do I have? 24. How many do I need? 26. Everywhere there's a pair of electrons between atoms, I will turn into a bond. Yeah? Does every atom have an octet? Yes. Is there any resonance? No. There is no need to draw resonance. So that parallel that Victoria was suggesting with it being O3, does that mean 3 resonance? No. Complete blind luck that it happened to associate that way. Okay? Kind of, sort of?
So you only draw lines if it's connecting with another,
Okay.
like, element?
When we draw lines, the point of a line is to show a bond. When it's not a bond, what do we show? Dots. Okay? There are other instructors out there or other methods. Okay, we're just going to look at that top, whoa, wrong marker. That top oxygen where people will go through and say line, line, line. What are they saying each line represents? A pair of electrons. Okay? They're just saying a pair of electrons. They aren't saying those are bonds. For them to be bonds, what would need to be next to it? Another element. There's not another element, so they know that's a bond, not a bond. Hudge. Okay? Problem with that is that's kind of confusing because now lines represent the same thing. Bonds and not bonds. Why does that become important? That becomes important when we move into the next category of Lewis structure, which is shape. And I have to differentiate the groups of electrons. Okay? So let's go through, and I'm actually going to do that line thing on the sulfur. Okay? For our shape, what we need to do is look at our center atom. Shape is always going to refer to a center atom, okay, or an atom of your choice. Typically, it's the center atom, and you don't get to choose. Okay? How many groups of electrons are around that center atom? Okay? To answer that, you look at each face of the square and decide, are there electrons there? In this case, there's 4. Every one of those faces has electrons. 1, 2, 3, 4. 4 groups of electrons corresponds to tetrahedral shape. Come on, that chart was up there for a good 5 seconds. You don't have it memorized yet? Okay, that's now the tetrahedral shape for that molecule. That shape becomes a bit ambiguous because there's an electron shape and there's a molecular shape. The electron shape says that all the groups of electrons are the same. Okay? Well, to figure that out, we could go back and look at our Lewis structure and decide, are all the groups of electrons around that sulfur the same? Well, how do you, line, 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 right? Aren't they all the same? This is why the line method is stupid. Right? Because what happens if we actually follow it the way that I suggested you do it? Are all four the same? How do we know that? One is literally dots and the other one is literally lines. Very clearly differentiates them. Okay? That's why drawing pairs as lines is a bad idea. Okay? This allows you to see that difference better. I do see you. Give me a second. Okay? So now what happens when I move up to molecular shape is I look at those electrons and I say they aren't all the same. And because they aren't all the same, they're going to affect the shape differently. Because what do electrons do when they get near each other? They repel. Each of those groups of electrons are trying to repel away from each of the other groups of electrons. That's the shape that we're getting. That pair that's just two dots is different than the pair that is a line. How do you know that? Really simple answer. They're literally different shapes. Two dots versus a line. Really simple answer. Okay? Let's take it to the next step. Here's two electrons. Okay? These two electrons are associated with me as sulfur. If I'm going to share them, what has to happen? I'd have to form a bond, right? Is it okay if we form a bond? What happened to the electrons? The distance between where those electrons are held on an atom versus shared changes. Right? In a bond, the electrons are further from the central atom. Because they're further from it, I can put more things around me. If they're closer, that repulsive force becomes stronger, and it's going to change where those other bonds are located. So I get a very subtle change to the overall shape. Enough so that I don't want to call it tetrahedral anymore. Okay? So what I need to do is evaluate those categories. So in this case, I have 3 bonding groups of electrons, and I have 1 non-bonding. What does that mean? Well, that means to me, because I spent the 5 seconds to memorize that chart, it doesn't take 5 seconds, that shape is trigonal, pyramidal. And that's it. Right? And some people might say, well, isn't that kind of arbitrary? What color is that? Red. Are you sure? It's not fire engine red? It's not apple red? Okay. We get all sorts of arbitrary lines. We could take it a step further. I actually think it's... You're like, that's not even a word. It's not a word in English. Okay. Language is entirely arbitrary. The words that we're associating with these shapes are intended to have some meaning. Trigonal, tri, 4, 3 bonding. Okay. Pyramidal. Why is it pyramidal? This is a fun one. In OChem, people talk about casting magic spells in the back on exams. There's a tetrahedron. The center is right there in the middle. There's a bond. There's a bond. There's a bond. I can't wiggle my wrist, but there's a bond. Right? That's a tetrahedron. If I take that and remove it from the picture, it's still pushing these bonds away. Right? So it's still that pyramid, but now I only have those 3 points. So it's no longer a tetrahedron, it's now a trigonal pyramid. Right? When you get to OChem, you can look funny at me, that's fine. You get to OChem, you'll be doing stuff like this. Like, people are wondering what's going on. You're changing your view on a molecule, but you were too cheap to buy a model kit, even when your instructor told you you should buy one because you need it. Okay? And instead you're using your hand. Okay? And it works. Okay? But what we're trying to get at is what those shapes are called. That's the point of them. Okay? So there were yes.
So because of the, it doesn't have a line on that side, does sulfur still have an octet or no?
Does sulfur have an octet? So this is winding back, but that's okay. How many electrons are in this line?
13?
Does sulfur have access to those? Yes. How many electrons are on the sulfur? 2, 4, 6, 8. Does it have an octet? Yes. Sulfur has the octet. Does that make sense? That is tricky because some people will count half the number of electrons in bonds. It's stupid. Don't do that. There's 2 electrons in a bond. Okay? So there's 8 electrons around that sulfur. Was it actually your hand or was it somebody else? Your hand. Okay.
Which one's bent?
I'll do bent in a second. We'll get there.
If there was 4 oxygens, would it be a tetrahedral?
If there were 4 oxygens, would it move to a tetrahedral shape? Yes. All 4 of those are now bonds. The bonding category keeps it as tetrahedron. There's no need to change the definition. Okay. Said I was going to get to bent, but before I do bent, I'm going to rewind a little bit. But can I delete? I think I heard a no. Did someone actually say no?
I have a question in regards to
Okay, yes.
so if it was SO3 minus 2, if it was SO3 minus 3, then like where would you put that random odd?
Where would you put that odd number electron? It doesn't fit.
So you would use it?
So it doesn't exist.
So you would use odd numbers?
No, that I won't go through. There's literally no place to place it.
Okay. So we just don't use it.
So SO3 minus 3
Doesn't.
doesn't exist.
Oh, I understand.
Okay? So, and this is something that people will like do. Well, let's create something. Let's see what happens if this. There are cases where we do run into odd numbers of electrons. Not in this class. I'm not doing that. Okay? It can happen. You still have to have a place to place it. There isn't a place to place it. We can't do it.
Okay.
Is there another hand about this? Okay, I'm on delete. And now's when everybody says no. Thank you. Remember we looked at this one, right? SO3. Why did this one suck? Okay, I'm just going to draw 2 of them. What question do you think I'm going to ask? What's the shape? How many groups of electrons are around my sulfur? 1 group? 2 groups? 3 groups? No groups. How many groups? 3 groups of electrons. And I heard someone say 4, I'll come back to you. If we had 3 groups of electrons, we have? Good. So now the question becomes, is it pyramidal or is it planar? With only 3, planar. To get to pyramidal, we have to have 4 groups of electrons. So this one is trigonal planar. Why is it not 4 groups of electrons? Literally, look at the face. Okay, I know why you want to say 4, because you're like, there's 2 lines there. Those 2 lines are on one face. When I ask for groups of electrons, I'm not saying how big the group is. You could put 1 billion electrons in that space. You'd probably get a Nobel Prize. I don't care. That's still 1 group of electrons. Okay? So it has no bearing on how many bonds or electrons are there. It's still 1 group. As long as we have electrons on that face, that's it. Okay? But we had a resonance structure, right? So don't we have to evaluate the shape for the resonance structure too? Man. It's the same thing. If you've done your resonance right, it's the exact same shape. If your resonance is wrong, you'll get a different shape. Okay? Because the atoms literally don't change their locations. It's only the electrons dispersing around that structure. So we'll get the exact same shape with resonance. Okay?
So for this one, are so you can't, we have an X.
One of those faces does not have electrons.
So the one you just deleted though, the SO2.
The SO3 minus 2,
Yes.
there was a pair of electrons there.
So why does that face that doesn't have, like, a bond have electrons, but this one can't?
Good question. Why does this one missing those 2 electrons, and why does the other one have it? What was the formula for this one? SO3. What was the formula for the one we deleted? SO3 minus 2. Where did the 2 electrons come from? That minus 2. That's why we had those electrons on the sulfur last time, is because it was a minus 2 charge. Here, not minus 2. It changes the orientation or the arrangement because we've literally changed the number of electrons. Okay? So we're going to throw in the bent shape now. H2O. How many electrons does hydrogen have? 1. That's an H. Let's try that again. 1. How many hydrogens? 2. Oxygen. 6 total. 8. Least electronegative would be hydrogen. How many bonds could hydrogen have? Only 1. It could only have 2 electrons around it. If I somehow did this, how many electrons does it have around it? 4. Hydrogen may be the least electronegative. It can't bridge. Your center atom still must be able to bridge. Okay, so hydrogen will never be a center atom, which means oxygen, even though it is more electronegative, will be our center atom. Okay, here's my box. I can now place my hydrogens wherever I want around this. So I'm going to place one here, and I'm going to place one here. And we're going to get at why, which is going back to your question here. Believe it or not, I haven't forgotten. I now need to place my electrons. Where do I want to place my electrons? Around the oxygen, starting between the H's. 2, 4, 6, 8, yeah? Yep, so we go through everywhere we had a pair of electrons between atoms, we turn into a line. We now have 2 bonds, yeah? Do all of our atoms have octets? Okay, so we got yeses and nos, okay? All atoms have their octet. Hydrogen caps out at 2, okay? So you could say no, because literally they aren't 8, but yes, hydrogen is maxed at 2. So there we go. Have we accounted for all of our electrons? Yes. So we're now asked to define shape. So when I go through and look at this shape, the first thing I need to do is evaluate the electrons. Are there electrons? Electrons? Electrons. Electrons. How many groups of electrons? 4 groups of electrons. 4 groups of electrons, all equally pushing away from each other, will generate a tetrahedron. So we end up with a tetrahedral shape. We now move to the next question, bonding versus non-bonding. How many bonding groups are there? 2 bonding. How many non-bonding? 2 non-bonding. That together gives us what shape? Bent. So what you asked about was bent. Well, there it is.
Thank you.
I'm hoping that was sarcastic. Does that structure look bent? No. Is it? Yes. Okay. What that is coming from is our electron geometry. There's your tetrahedral shape, right? Okay. Tetrahedral shape. One of those groups is the electrons. We'll make that my wrist, so my wrist can disappear from the argument. I still have the other 3 groups, right? Now I got to remove one more pair of electrons, right? Oop, not that one. What's the shape? Bent. What's the shape if you look at it from this? Particularly if you're looking at it from a 2-dimensional drawing. That looks awfully linear. Okay? Lewis structure does a crap job of drawing shape. Okay? What it does is show that the bonds are there, that there are non-bonding pairs there. What you have to do is layer on top of your Lewis structure that information about shape. So now we can look at that and say, is that a good way to represent the 3-dimensional molecule of water? No, because the 3-dimensional molecule of water is bent. With that extra information, I might go back and say, actually, I should be drawing it like this. And when you look up the Lewis structure of water, how is it typically represented? The nice pretty one where it's showing the bend. What we're trying to represent is that three-dimensional shape better. Lewis structure does not show that three-dimensional shape.
So on an exam, which one do you want?
So on an exam, always a good question, day before the exam, 2 days before the exam, what would we expect? What I expect is that you know what Lewis structure is, and you know how to interpret what the shape should be. Do I expect you to double back and change your Lewis structure to better reflect the three-dimensional shape? No. Okay. What I would expect if I asked this, provide the Lewis structure and shape for water, you would draw this thing, okay? You would tell me 4 groups of electrons, which meant tetrahedral. You would tell me 2 were bonding, 2 were non-bonding, and that together means bent.
Do you want all the circles, like, that, like, show the bonds?
Okay? So it's good. Probe the level of where you need to answer the question. Okay? That question that I asked to do all this was that one question. That was, what's the Lewis structure? What's the electron geometry? What's the shape? That was actually 3 questions. Okay? If you can't figure out the Lewis structure, can you figure out the shape? No. Okay? So in a show your work type fashion, that sucks. Right? Because now you lose points for Lewis structure. You lose points for electron geometry. You lose points for molecular shape. That would be a very painful hit to your score. I try to segregate questions so that that does not happen. So what you would see this be is draw a Lewis structure. Because I'm not going to do a multiple choice, draw the Lewis structure. Because you could probably reason through your answer choices and just eliminate things. So I'll give you a formula and say draw the Lewis structure. Okay? That's show your work. In the multiple choice, I might say, what's the electron geometry of water? To answer that, what would you need to do? Draw the Lewis structure. I'm not giving you points for that. I'm only giving you points for the shape, right? Or the electron geometry. But since it's multiple choice, there's less point involvement in it. You lose less points to your overall exam grade. Kind of, sort of? Okay. More questions? Did that actually answer all of your bent stuff now? Yeah? Okay. Brandon? Because you had a hand? And then I bounced back to, I think, Christian, right?
You answered my question.
Oh, I did? Okay.
That was a lot better.
Okay. Short attention span. Squirrel. Next. We good with that? Okay. We can do more practice here in a second, but I do want to get to this slide because I think this slide is really important. Remember how I said you should purge information? This is stuff I think you should purge. Okay? So when you get the exam and I say go, you should open up to your periodic table and you should draw this information onto your periodic table, minimally. Okay. You have to use what I give you. Okay? So this is why I recommended that when you're doing your studying, what should you be using? The exam that I give you on the, or the periodic table that I give you in the practice exam. So you're used to working with that format so that you can find that information swiftly, efficiently. If you get that information purged onto your exam, now when you see a question about electronegativity, all you got to do is go back to your periodic table where you drew the answer and just interpret your answer. There's no extra thought steps that have to happen. Oh, which way was this or that? It's there. And because you did it at the beginning of the exam, you're more likely to be correct. Halfway through the exam, your brain is numb. You're probably going to have screwed up the trend. Make sense? Okay. You might screw up remembering valence electrons. Okay. So if you get that down, you're good. Kind of, sort of? Okay. Next thing I want to throw out. So when we start the exam, we got your names. You write your name on it. You'll write the names of the neighbors near you. Some people ask, why do you want the names of the people around me? It's an anti-cheating device. If you get called out for cheating, all I got to do is pull out your exams, look at the people next to you and be like, yeah, you totally did. You literally just copied across from the person next to you. During the exam, I will also go through and build a seating chart while you're taking the test to cross-reference that. This is why I know your names. Okay? So please don't cheat. Okay? I really don't like catching cheaters. Okay? So get that set up. So you got your names on it. Now I say go. Now what do? Well, arguably the directions were already there. You could probably get away with reading the directions without me telling you to go. So while you're writing down names, you could read the directions. Which is a good idea. You should read the directions. Maybe people that have looked at the practice exam know why you should be reading the directions. Okay, just letting that sink in a little bit. Okay, next part. Flip to your periodic table. Purge. Get that information down. How often do you think you're going to be referencing the periodic table in a chemistry class? A lot. It's stapled to the front, right? Tear it off. Tear it off, flip it over so you can look at the periodic table the whole exam. Okay, you don't have to look up there. It's all that information is on that sheet in front of you. Okay, now what can you do? Start the exam. Okay, that's cool. Which question do you start with? Okay. And this, interestingly enough, is a really big thing for a lot of students, particularly in chemistry. 90% of the class is going to start with one question. The very first question. Okay? Which could be a very good question for you to start with. But what if that first question is something you know nothing about? That is a useless question to be looking at. As soon as you acknowledge you don't know, move on. Do not continue to stare at questions you don't understand. Okay? Your first question answered is the first question you know the answer to. Okay? That could be question 1, that could be question 39. You should scan through the entire exam to find that one question. Okay? This is a strategy that everybody uses through their daily lives. You go into the emergency room. Okay? You dropped a bowling ball on your foot. It hurts. How long does it take you to have a doctor take a look at it? Really long time, because the dude behind you is having a stroke. Okay? The nurses are like, yeah, get out of the way. We need that guy. Okay? We triage according to what we can fix and best do. That's what's happening with our exams. Okay? So do it that way. Okay? This will suck. Okay? Not just because it's a test. Because you will have spent the first maybe 15 minutes of the exam writing down all the answers you know. What do you spend the last hour of the exam doing? Spending on all the questions that you don't know. You will spend all of that time looking at questions that you didn't know. When you walk out of the test, you will feel massively depressed because you just spent all that time on the questions you didn't know answers to. What you won't remember is that you answered all of those questions you knew. And those are actually increasing your grade. If you scattershot it, what happens is you get out of the test, you're like, oh, that wasn't too bad. You know, I answered questions all over the place. But you spent 5 minutes on a question you weren't going to get the answer right to anyway. When you could have spent those 5 minutes answering 3 questions that you did know the answer to. Make sense? Okay. Questions? Do well. Right? It's just like that. Just do well.
Oh, okay.
See? He got it. Okay. I can do more Lewis. I can do more anything you want. Except tap dance. I don't know how to do that. Shuffle off the buffalo. I think I learned that once. What do you got?
Why is hydrogen energy 2? Energy level 2?
Is hydrogen energy level 2?
It's 1.
No, it's 1.
But before you said it was 2. Unless I misheard you.
You probably just heard how many times you did it.
That might be what that was. So if we're referencing hydrogen, awesomely not on this periodic table, that's cool. Sort of, yeah, but that's the key. Hydrogen would be here. That is energy level 1. Okay? How many electrons can I fit into energy level 1? 2. Energy level 1 corresponds to this whole section. How many things are populated in that section? 2. 2 electrons. How many electrons can I fit into energy level 2?
8.
There's energy level 2. There's so much crap on this. How many things are populated in energy level 2? 8. So I can fit 8 electrons. It does get a little bit wanky when you move to the next one because energy level 3, you might be like, well, doesn't it only fit 8 electrons except? Remember the d orbitals are offset? You'd have to include them. Okay, so you'd have to remember that offset to realize your third energy level actually gets you up to 18. Okay? I see you staring at it. Do you have a question?
I just gotta remember that off.
And so there's a lot of facts that can get tossed out here. We got lots of numbers showing up everywhere. All of those numbers, for better or worse, are on the periodic table. So those patterns are there. It's a question of, did you decide to learn where those patterns were, or did you decide to memorize that fact? You're going to have to find a balance between both. What else we got? No other questions? Draw CO2. Lewis structure for CO2. Have you got questions? We'll walk through the CO2. And I've also got another one up there, SO4 minus 2. So if you already think you got CO2, you can move on to SO4 minus 2. Carbon has 4 electrons. Oxygen has 6 times 2. 12 and 4 would be 16. Carbon, center atom, oxygen, yeah? Okay. Place my 8 electrons. Yes, hand.
Isn't oxygen more electronegative?
And therefore, which atom should be in the middle? The least electronegative. This is maxes and mins go all over the place. This is why it's very careful to have that stuff written down. Okay, so I'm going to place my electrons around the oxygens first. There's 8. There's 16. Okay, I did see one example where someone was immediately bending it. Don't bend it. It's a square. Put them around a square. Don't start bringing in shapes like trying to predict that it's bent. Don't do that. Draw it on a square. Make sure you're good at Lewis structure before you start layering in all sorts of other crap. Okay, and ultimately that other crap you don't need for this class. Okay, so keep it simple. Okay, everywhere there's a pair of electrons between atoms, I can turn into a line to represent a bond. Yep. Does every atom have an octet? No, so what do I need to do? I need to move a pair of electrons from an oxygen to make a double bond. So there we go. I'm going to make a double bond right there, yeah? So far, so good? Yes. There's 6 electrons now around the carbon. How many does it need? 8. So what am I going to do? How many electrons around each oxygen? 8. How many around the carbon? 8. Does this satisfy all your rules? Yes. Is this a valid Lewis structure? Yes. Okay. But it's ugly. I don't care. Okay? It satisfies all the rules. You're going to get the exact same answer as far as shape and everything else. That is a valid Lewis structure for CO2. And where people will go, but that's not the Lewis structure. That's not the accepted Lewis structure. This is the accepted Lewis structure, right? Why is one better than the other? Easier to learn. Not only do you have to understand octets and all of those, you have to say it has to be symmetric too. You're going to add a rule and say that's easier to learn? Because if that's the case, you just opened up a real big can. And I can make up all sorts of fun rules. Okay? Why is one different than the other? You don't know. Does that sound a bit scary? Yeah. You have no reasoning to explain why the bottom one is better than the top.
Would it be that the connections need to be far enough apart from each other? They need to be evenly distributed?
Nope. That's back to a symmetry argument. There is literally no rule that you guys have access to that would explain why one is better than the other. Okay? Is there a rule?
Probably.
Yes. That rule is discussed at greater length in the play posit video in the section you're not responsible for. Okay? Which some of you may have to play through anyway. Okay? It is discussed in length in 151. It is discussed in length in OChem. You're not in those classes. You just need to satisfy the minimum set of rules. This is why Lewis structure becomes a challenging subject to deal with, because when you are trying to figure out if your answer is right, where do you go? To the internet. And what is the internet going to give you for Lewis structure? The OChem understanding. You're not at the OChem understanding. You're at the fundamental understanding. Be careful using the internet to find answers. Okay? Really want to emphasize that when it comes to Lewis structure. So much so that there's a lab that I think you do next week on Lewis structure. Okay? I yell at adjunct instructors who overteach Lewis structure. Okay? Because it is a big, big freaking issue when you move into OChem. Why would I have you do SO4 minus 2? Because it introduces the exact same issue. If we draw SO4 minus 2, electrons on sulfur. 6, oxygen. 6, there's 4 of them, right? Charge. Total. Sulfur's in the middle. Scatter my oxygens around the outside. Yes? That was the wrong eraser. Make bonds. Does every atom have an octet? Yes. What should you be doing? And unfortunately, I can't now grade it this way because I haven't been talking about it enough. Because it is charged, we need to specify that there is a charge in our Lewis structure. We just do that by putting brackets and a charge in the upper right-hand corner. If you look up the Lewis structure for SO4 minus 2, this doesn't show up as a valid answer. Why not? You don't have the rule set to explain why not. So be very careful using the internet with Lewis structure because it will over-finalize your answer. I will harp all over that. Okay? Make sense-ish? Use the rules you have at hand. Okay? With that, we got to be done. I see your hand, so I'm coming up there.